Year of lensing, professor also here in Groningen, director of the Captain, and I think also classmate in high school, since high school with Henk. So we should all ask information about this high school. And okay, so Leon, the floor is yours. I think we will hear about tensions between the early and the late measurements.
Yes. So while this is being set up, I mean, I'd like to thank especially the organizers for organizing this and then inviting me to give this talk today. And actually last week we were here on Friday and we talked about in this actual dome about the last 100 years of our institute. It is exactly this past weekend, 100 years ago, that Jacobus Kaptein, the founder of our institute, passed away. And we thought it would be a nice moment to remember and to think what happened in the last 100 years in astronomy. And that's really, really amazing. So, so it's wonderful to see, to jump from last Friday to look at the history and see where we are today. And Henk already gave a wonderful, I think, introduction of where we are, that we know a lot, but in some sense, we are also ignorant about the universe, right? We are now in an era where we can measure things very precisely, but the question of accuracy remains. And that increase in accuracy or in precision is actually leading to tensions in cosmology. And whereas Henk has focused largely on the weak lensing that Euclid can do, Euclid is also a telescope that can find many strong gravitational lenses. And that is the field that I work on. And we are trying to measure the expansion history or the expansion rate of the universe, the Hubble Constant, Hubble lemaitre. And in that particular area, we are finding tensions between various measurements in the late and in the early universe. So I will talk about this. Good. So, so we have this wonderfully working standard flat lambda CDM cosmological model that seems to explain things to, well, almost anything on the very large scales with only 6 free parameters. But due to this increased precision, right, some cracks are now appearing in this model. Right, and just for those in the audience that are not very familiar with cosmology and where this information comes from, here you have, of course, the cosmic microwave background. Right, it's a baby picture of the universe that is giving us a tremendous amount of information about the shape of the universe, the expansion history. Of course, some of these parameters are mixed. They are not all, let's say, measured in a space that is orthogonal. So there's lots of correlations and degeneracies. But this is one of the treasure troves of information where we are measuring these cosmological parameters from. Right, and this cosmic microwave background is compressed in this power spectrum here, and you can see that this standard cosmological model fits the data almost perfectly. Well, it fits it basically perfectly. Right, there are very few, I think, models in physics that fit the data this nicely. On the other hand, so this is what we call, let's say, early universe, right? This is happening very close to the Big Bang. On the other hand, you can measure the expansion history of the universe and also some of the cosmological parameters with standard canals, in this case, for example, supernovae. And of course, this led to a Nobel Prize, right? But you can also see that the universe is not our universe that is matter dominated. Of course, this we have known now for more than 25 years, right? And also the amount of data and the precision of the measurement is increasing drastically. Now, Henk already showed images of formation of structures in the universe. And again, if you run those models with those standard ingredients that Henk was talking about, dark energy, dark matter, and baryons, you can also fit over a very wide range of wave numbers and scales in the universe with many, many different probes, the power spectrum of the universe. And again, this fits extremely well. So, right, everything works, right? Let's move on. Right, it all fits together in this little point here. If you look at the various matter and dark energy densities of the universe, and you have this line here, which is a flat universe, it looks like all the ellipses overlap there. And that's more or less where we were probably about 5, 6, 7 years ago. Right? The errors were still large enough that this sort of combined circle had still a statistical error on it that sort of agreed with most of these measurements. Right? There's clearly overlap between all of these measurements. Now, what is the Hubble constant? Right? So the Hubble constant, right, gives you the expansion history of the universe. So that's another way, right? There's another. In some sense, you can measure omega matter, omega lambda, and some of these things without actually knowing what the size of the universe is and how fast it is expanding, right? The Hubble constant sort of calibrates some of these models. So you can change the Hubble constant, and let's go back to this one here, right? The shape will not change, but it will, in this case, move up or down. So your universe becomes larger or smaller. So the Hubble constant is another thing that you can measure from the data if you have standard rulers, standard candles, or in the case, as I will show, standard, let's say, time with strong gravitational lensing. Right, so you can have many expansion histories of the universe, right, that at this moment in time give you the same derivative of that history, which is the Hubble constant. Right? So you can measure the Hubble constant locally here, but you have many, many histories that can give you that same derivative, and that depends, of course, on these values of the energy density and of the universe. So if you measure things in the nearby universe, you're measuring it somewhere here. If you measure it early on, maybe with the CMB, you are measuring things here. So in order, right, to get the number here, which is the definition of the Hubble constant, you need to know that expansion history. In some sense, you are interpolating or extrapolating or predicting or post-dicting, but you're going from a measurement here to something here. And of course, things can go wrong. So if you're comparing things here to things here, you better get that history right. And that is exactly where the tension is now appearing. So let me give you a bit of an overview of the Hubble constant and why this problem is appearing. And this is exactly what Henk was alluding to, right? These tensions appearing because of this accuracy versus precision. The error bars are shrinking. This is just an example of Schu's at supernova measurements. So that sort of plot that I showed earlier of this upgoing curve. And these are the errors as function of time in this particular project by Adam Rees, right? And you can see over the past 20 years how the errors have been decreasing, or how the errors and the systematics and everything has been gotten under control. So in all various, these are different sort of measurements and things that can go wrong or they need to be calibrated, and the errors, if you just add them quadratically, are quite large 20 years ago. But we could already see then that the universe was not like matter dominated in here. And now the errors are so small that you can get a % accuracy or sub% accuracy. Now you think that's great, right? So then let's see what happens to that Hubble constant over time. So you see, of course, that if you measure it with these Cepheids, in this case, to calibrate the supernovae, you see that over time, the actual value is not changing that drastically. It's somewhere between 70 and 75, but the errors are quite large and are shrinking to where they are these days, about 1%. Right? And they sit at roughly 70 and right, 73 here. Now, if you do it slightly different to the tip of the red giant branch, you get here the errors. But if you look at the cosmic microwave background, you're doing this early on in the universe, then you see this happening. So here they agreed, and certainly within the errors, but even maybe in their value. And then suddenly there is this drop here that was going from W map to Planck. And the errors, of course, shrink. Planck is so precise. It has extremely small error bars. And the difference between these is largely in the way that you add higher order modes in the power spectrum, but also you get more control over foreground removal. And now you see that the error bars are so small here, everything seems to agree, but somewhere around sort of 2015, things started to diverge. And this is called what we are now calling tension. Now, it's not just there in the Hubble constant, right? So this is an overview in a recent review paper that I'm also part of. Very, very large overview paper of all the values, well, maybe not all of them, but most of them of the Hubble constant between late and also, right, so these are the cosmic microwave background measurements and, for example, baryonic acoustic oscillations, which are all sort of early universe measurements. They come from the same physics. But then if you go to things like the supernova, or what I will talk about, strong gravitational lensing and other measurements, you see that they are mostly aligning here. Now, this tip of the red giant branch, some of these measurements are shifting a little bit. I think that's these ones, but even I cannot see it from here. But you see that there are basically two groups, some here and some here, and right, they are actually quite far apart. But that's not the only tension. For example, from weak gravitational lensing, as Henk was saying, you can also measure this particular parameter, and also there you see that they are not lining up. So that's another tension. Now, of course, these parameters are coupled. You cannot measure necessarily these ones without knowing this. So there is some covariance between them, and that is marginalized into these error bars. But there's clear tension, right? And that is because the error bars are shrinking. And this is just another way of looking at it. You see the CMB versus the Cepheids. This is right the big discussion between these, and there's also right other measurements. So now you have these two sort of ways of measuring things. You have the CMB, you have the supernovae, but yeah, who really understands supernova physics, right? Right, all the calibration that is done in this is often, I mean, there are some geometric methods, but there's often a sort of more empirical calibration necessary here without really fully understanding the physics. There's dust involved and all kinds of corrections. Of course, right, everybody does an excellent job and try to convince themselves this is all, they're doing the right job, but yeah, who knows? So, right, is there another method? And that is where we have come in with strong gravitational lensing and measuring the time delay between lensed images. And the time delay between lensed images, I will show some examples, multiply imaged quasars, that time delay is a measure of the size of the universe, right? Very simply said, if you have two images of the universe, of a quasar, and you measure a time delay because light travels a different potential and a different path, if you scale up the universe, you make it bigger, then also this time delay gets larger. So it's a very simple way of measuring the size of the universe. And if you measure the size of the universe, you have a handle on this expansion rate H0. And it turns out that that measurement is rather insensitive to these other cosmological parameters. Now, tomorrow at the conference dinner, right, you might get familiar with this particular image here of a wine glass, right? You might say after a few glasses of wine, you might point the bottom of the wine glass at a light, and you will be able to see multiple images of that light, and in some cases rings or double images. So that's the basics, of course, of lensing, right? Geometric lensing, but gravitational lensing is not that different. You can write strong gravitational lensing in GR in a way that is very similar to optical geometry and lensing by, for example, a wine glass, by turning that gravitational potential into an effective refractive index. So strong gravitational lensing is not that difficult. I probably shouldn't say that. Right, and this is a beautiful example. Now, this is not one where we measured time delays, but this is a beautiful example. I think it's still one of the most beautiful examples of a strong gravitational lens. But the ones that we are looking at is these types, where we have a galaxy, we have multiple quasars, which are gravitationally lensed by this foreground galaxy. Right, and as I mentioned, these quasars, they can vary in brightness, and you measure their light curves, and you see that the light at these various quasars arrives at a different time at the observer on Earth. And the longer that time delay is between these images, the bigger the universe is, and the smaller h0. Right, just to zoom in. Right, and the idea is the following. Again, you have the lens, you have your quasar, light travels different paths, not just geometrically. You can measure the distance between this path and that path, but this path is also going through a deeper part of the potential in this one. So you need to take that into account. And both of them are set by, of course, their distance, relative distances, but also the potential. So you need to know the mass distribution of the lens. If you can measure all of these things, you can measure what the time delay is, and therefore infer this to constrain the Hubble constant. And that is all captured in a very simple equation here, where you have a geometric term. Here you have a potential term. So once this is known, also this can be calculated. Right? These are redshifts here, so this can be measured with spectroscopy. And then you have this term here, which are the angular diameter distances, and this is proportional to the inverse of the Hubble constant. Right? So this time delay measurement would give you a measure of this if you know things like omega lambda, omega matter, etc. But it turns out that this is not very strongly dependent on those parameters, and that's the strength of this method. So why didn't we do this 25 years ago? When I started my PhD, this was my PhD project, to measure a time delay for the very first time in h0. And after, right, nightmares, let's say, it turned out to be very difficult. And the reason is that, right, time delay measurements were extremely difficult and not very precise. The mass models were too simplistic in those days. Right, we had very simple models for the environment of these lenses, because of course it's not just that lens that does the lensing, it's the entire mass distribution around it, and also the mass along the line of sight. And in the past we had these very, very simple models for that, and in the present day we can measure those time delays much more precisely. We have much more sophisticated modeling techniques, and we have much more data and more sophisticated ways of modeling the environment of these lenses, and also the line of sight contribution. So what I will show is the result of a combination of two programs, Holy Cow, yes, I didn't think of the acronym, and Cosmograil. This one does the lens modeling, this one does the time delay measurements, which are two very, very different of course, problems. So these are the lenses that I will show the results of. These are six gravitational lenses where all the time delays, or the time delays, have been measured. The mass models have been constructed. The fields have been characterized. Redshifts, everything is known. Kinematics is measured as well. This was one in my own PhD thesis a long time ago. And I must say, the Hubble constant that I measured from that system has not changed since. So I did something right, right? So these are the systems again. So first, ingredients, right? I showed you those four things. Ingredient number one is, of course, if you don't measure a time delay, you won't measure a value of the Hubble constant, right? So I will show you an example of a measurement of light curves. and just look at the number of days here, right? So this is, I don't know, a few PhD theses stacked on top of each other. These are long-term 10-year programs to measure these light curves and measure the time delays. Nowadays, with better telescopes, you can look at micro fluctuations as well. So you can, for example, zoom in on this here, and you can do very small scale fluctuations and measure the time delay extremely accurately. So nowadays we get those time delays much faster than we got them 10, 20 years ago. Because we get access to larger telescopes, and in those days people said, well, if you want to monitor these things, right, please go ahead, but use a 1 meter telescope. Right, we're not going to give you 2, 3, 4 meter telescope, but if you give somebody, right, a 2.2 meter telescope to do this, it's much more sensitive. You can actually measure it much faster. So that's just one example of how, right, the quality of the data is. The other one is, of course, constraining the mass model of the lens and the nearby companions. Now, just again, this was the data not that long ago from the ground, right? Then, of course, in the 90s, Hubble Space Telescope came. This is the quality with the Hubble Space Telescope, and this is the quality we get with Keck adaptive optics, right? Extremely high resolution. This is, I think, 60 or 70 milliarc second resolution. This is comparable. No, this is actually better than that, I think. So it's a huge improvement in data quality. Besides that, techniques that I have developed with my students and postdocs and collaborators is to combine this with stellar kinematics. So you have, of course, those gravitational lens information, but you also have kinematics. And both are a measurement of the gravitational potential, and you can combine them in a joint analysis. Right? If you predict some mass model from lensing, you better predict the correct kinematics or vice versa. And of course, in the end, you combine the two to constrain mostly the density slope. So if you change that density slope, you in general don't change the mass very much within that Einstein ring, but you do change the kinematics. So that kinematics is sort of a measurement of how steep your density slope is, and the density slope sets the time delay largely between the images. So that was a very powerful method to break degeneracies in these models. Now, the environment is not as easy as you might think, right? If I show you those nice zoom-in images, you think, oh, that's a nice isolated lens, right? Pretty straightforward. But if you go a little bit deeper, you see that, of course, if you have a massive galaxy sitting somewhere, there are other massive galaxies sitting around, right? These things live in groups or clusters, but if they're a cluster, we generally sort of don't bother with them. But they certainly always live in overdensity, so you need to model those as well. And we take those along, we measure their kinematics, their redshifts, and we try many, many different mass models right, to fold in their contribution as well. So that's a huge improvement as well over the past 20 years. In terms of mass models, techniques that I have also developed together with collaborators are so-called grid-based modeling techniques, where you take this image here and you can maybe subtract the galaxy light here, but then you still are left with the lensed images. And then you do a complicated inversion method, nonlinear linear inversion method to get the model of the source. And then in this case, of course, you have quasars in them, so you model them separately and you add the two together, you subtract it off from your observations, you get some residuals. And then, of course, you optimize the parameter in that model to get the best mass model possible. And this is a very, very powerful method to squeeze all the last pieces of information out of the data. So that has improved our mass models drastically. Last but not least, the line of sight, right? You might think, well, it's mostly dark matter. Yes, you're right. But as Henk has shown, you can shine light on dark matter by using weak gravitational lensing, but also counting just the galaxies along the line of sight. And if you do that, you can predict the contribution of the line of sight surface mass density for, in this particular case, a lens here, and they agree with each other. And this is a weak lensing measurement. So we can also control that as well. So let me then move on to the results, right, of all of this on these 6 gravitational lenses. When we throw it all together in a Bayesian machinery, with the cosmology, right, with the lens model, the kinematics, and every uncertainty that we know. We're also trying to do this in a hierarchical Bayesian sense in the future, but it's very expensive. So currently these measurements are independent from each other. But we can tie those models together as well if we say, right, okay, there is some common parameter that depends, let's say, on galaxy mass. But that's for the future. Yeah, just want to say one more thing. Of course, we assume many different mass models for these lenses. So it's not just that we grab one from Binney and Tremaine and go with it, right? We are trying many mass models to get measurements, and we do it blindly, right? So when we do the analysis, etc., we don't know what H0 is coming out of it until we've written the paper, and we do a unblinding, where we push a button and H0 appears in the paper, and then we push another button and we submit the paper. Right, so these are all models, and you can see, right, they are, of course, they have been sort of normalized, but you see there are some differences between them, but it's not drastic, and we marginalize over those various models in H0. So what's the outcome? Now, this is the first lens, again. This was, this is the one that was also in my thesis, and this was the value. Now, I must say, for full disclosure, this was the only lens that we did not do blindly, because it's the first one we did, and then we decided, yeah, maybe it's better if we do it blindly. But this is the value that came out. Now, the next one we did blind. So that's the blue one. We added that, and this is the combined likelihood. Or posterior. Next one, next one, next one, next one. And this is what we published in this milestone paper of Holy Cow 2 years ago by Wong et al. And we can see, right, this is a value that compares extremely well with the late universe measurements of supernovae, etc. Now, we added an extra lens from another survey, but it doesn't change anything. So this is based now on 7 lenses, and you can see, right, a value of about 73 with a, or 7, close to 74 with an error of about 1.5 kilometers per second per megaparsec. Great, fantastic, right? So how does that compare with Planck and BAO? And again, you see a more than 5 sigma tension. Now, what I showed you has an assumption in it, and it has an assumption that the kinematics of these lenses are anisotropic. So that means that there's no particular, let's say, preferred elongation of the orbits of the stars. So if you get radial orbits, things go a little bit more like that, and if you get more tangential orbits, things are a little bit more, let's say, on circular orbits. We know from nearby kinematics of massive ellipticals that the inner regions in general are very isotropic. So this is what we assumed in this analysis, but right, you might want to do a little bit better than that by letting that go free as well. And this is exactly that point that Henk was making, right? When some of this sort of astrophysics comes in, right? Okay, what orbits do your stars move on? If you change those orbits in the same potential, you get different kinematics. On the other hand, right, you can also say, okay, right, so you don't know what it is, you're assuming the wrong kinematics, and therefore you're inferring the wrong density profile. And that is largely, this anisotropy is largely degenerate with the anisotropy in, or the radial anisotropy in these massive elliptical galaxies. And again, massive elliptical galaxies have been studied in the nearby universe, right, extensively, including their anisotropy. But it's much harder to do when they are at cosmological distances. So we're a little bit literally in the dark there until we get measurements, and we are, right, we have shown, for example, how many measurements do we need, and right, with what data, and with JWST, which is of course just been launched in a month's time. The first data release show will be had again in this dot theater on JWST first data. We have a big event here in Groningen, and in the other institutes in the Netherlands in astronomy are having the same. But that particular telescope can do integral field spectroscopy and measure spatial resolved kinematics of these lenses. Now, we've done that 20 years ago, but not on these lenses with very bright quasars. With bright quasars, you need very, very small point spread function. Otherwise, this light will outshine your stars and you can't measure the kinematics. But with what we have now, you just want to focus on this point here. You see if, now this is a bit of a strange parameter, but if this goes to infinity, effectively within that radius, you assume your kinematics to be isotropic. Right, and then you see you converge to that value of 73, 74. But as you make that number smaller, that means the radius where you go from isotropic to radial anisotropy moves further and further in. The value of H0 drops a little bit. So if you take that into account, the errors become larger because you're adding an extra ingredient and an extra uncertainty and you're marginalizing over it. But also depending on which prior you put on the kinematics from various data sets. That again, this is a large program I did about 15 years ago, and we put these as priors, but you can do different assumptions, right? They all have the same or they don't all have the same. You get a slightly shifted answer. Now the error bars are larger, so these are statistically consistent with each other. But of course, right, this is accuracy versus precision. You have shifted your value systematically to a lower one. And the big question now, and that we are dealing with and that we are trying to resolve, is to figure out what is the kinematics of these lenses. Are we here or are we here? And JWST can help with that. And this is basically showing that I think the same thing. So let me move on. So this is what we can do in the future when we get more lenses, right? And even have these uncertainties, right? When we go to samples, for example, of 40 lenses, these errors will shrink here to less than 1 kilometers per second per megaparsec, including the kinematics. So that's where we want to go into the future. And a satellite like Euclid will find 5,000 gravitationally lensed quasars. So that's going to be, again, a treasure trove for our field. Of course, kinematic, time delay and kinematic follow-up is still needed. But Euclid itself will already provide the lensed quasars and the information about the lensed sources, and also partly the redshift information. So in the last 1 minute, I see. Now assume that this tension is real, right? How can it be alleviated? Imagine that indeed, right? We find that the lenses are isotropic in their kinematics, so we really have this tension. How do we alleviate it, right? And we're still in that thing. Can we do that with gravitational lenses? So, right, so we can change the cosmological models. That is what we did in that particular paper that I showed by Wong et al. We went through all of these models and we ran the whole Bayesian machinery for all of them. And this is the result. And this shows exactly why strong gravitational lensing is so strong, because you can see how degenerate, for example, Planck is between H0 and the flatness of the universe, whereas our measurements doesn't depend on that almost at all. So you see that tension, right? And if you make the open universe, and we already know this, right, you can change the values of the Hubble constant, but you have to push it in this direction, right? So you can't have this flat universe. So this is probably not going to solve the problem, except if we accept the universe is not flat, right? You can change the equation of state. I'll go through this very quickly, since I already ran out of time. Right, you can change, of course, the equation of state and have the W parameter change itself. And again, right, you're always sort of straddling these contours here. There's never really a massive overlap. You can change the effective number of relativistic particles, like neutrinos, for example. Right, again, right, it might help a little bit, but not a lot. So we've done all of these tests. So, and it turns out that it's extremely difficult by changing, at least within the scope of these models, to get the CMB and BAO in agreement with strong gravitational lensing, largely because we're actually not that sensitive to these parameters. We have a very robust measurement. So just to summarize, right, strong gravitational, strong lensing time delays provide an absolute distance scale and direct measurement of H0. Now direct, but of course there are ingredients in there, but it's sort of a, right, an integral measurement of the time delay of the universe. There's not like step on top of, on top of, on top of, on top of, and it's not a distance ladder. And it's independent of distance ladder measurements and CMB and BAO measurements. So I think we think it's a very strong added methodology to this big question about tension. We're measuring time delays to a few % accuracy in a very short period of time. Right, there will be many more of these lenses. Right, these are only a handful that can be done now, but very soon with all of these missions here, particularly Euclid, there will be hundreds, if not thousands, of new lensed quasars coming. So of course, time delays have to be measured, and the kinematics have to be under control. Currently, we have this without kinematic anisotropy. And yes, so this is just where we are at the moment, and I'd like to thank you for your attention.
Yes. Thank you for this very nice talk. I see already a question there in the audience.
Works? Yeah. Thanks, Leon. That was very interesting. What about the mass resolution of closer to the, okay. The mass resolution of your models, your lens models? Do you go down to 10 to the 6 solar masses? So can you explore the things that Charlie was asking, substructure? Can you tell whether this will shift the value of H0 or still keep it?
Yeah, that's a very good question. So, of course, we have another branch in our field, which is, I'm also one of the people that developed those techniques of gravitational imaging. So you can use those images to actually look for perturbations in the lensed images due to substructure. They are sensitive to about 10 to the 8 if you use these HST images. You can go down to 10 to the 6 and lower if you go to quasar flux ratio anomalies. Of course, you need to disentangle them from the variations themselves, but they're not very, they don't impact the time delays that much because it's really a 10 to the 6 on 10 to the 12 solar mass galaxy. So it's a 10 to the -6, 10 to the -5 effect. So in general, we can ignore the effect on the time delay. We can't ignore the effect necessarily on the indirect effect that it might change the surface brightness of the lensed images or the quasars, and therefore the modeling might be biased, right? But that's why we also developed these gravitational imaging techniques where we actually do a perturbative potential correction on top of these models and correct for those effects. And in general, they're not very large. So we're not yet in the regime, but probably once we hit that 1% regime, we need to start worrying about this. Yeah.
I see another question up there.
Yeah, the kinematic anisotropy problem. Could you address this by just taking an unbiased sample of the sizes or the shapes of clusters in various all over the sky, and then seeing, are you or are you not selecting your good time delays so that they have a spherical projection, and that you're therefore choosing ones that are either really spherical or really circular, or that are elongated in the direction so they appear circular? Can't you do that analysis? Wouldn't that be the type of analysis you would have to do to correct for this kinematic anisotropy?
Well, I mean, we have, for example, used the Eagle simulation to do strong gravitational lensing simulations, and there statistically you can figure out whether you're sort of like picking up oddballs. It doesn't seem to be the case. But the problem is in those simulations that probably in that inner region, you wouldn't trust the stellar kinematics in the simulations that much. So what we think is a better approach is, of course, to measure it with kinematics. We can just see what's happening. The other one is to select what we call a parent population sample, which, for example, in nearby universe, where we can measure it, and then use that kinematics as a prior on our analysis. So those are two different approaches. We can use other similar galaxies in the nearby universe where we can measure these things exquisitely and say, we can just exclude those kinematic models. But of course, the best is to actually measure it. But doing that at the redshift of 0.5, 0.6 with bright quasars requires things like JWST. But by having elongated things along the line of sight, yes, we would that would show up in the kinematics as well. But from sort of simulations, we don't see that that's a real issue.
But it does seem to be the case that your parameter, your anisotropy parameter, which you showed on the y-axis, as it goes smaller, the shift, there was a pretty large shift in H0 to lower values.
Yeah, from that 73 to
Is there
sort
an
of
easy way
67.
to understand that? I don't quite have a good sense.
Yeah, if you take your kinematics, so let's say if you take the same mass model, but you change and you have a particular kinematics, you effectively, what you're doing is you're tilting your velocity dispersion as function of radius. So it drops off in a particular way, but if you change the anisotropy, it drops faster or less fast. But if you change the density profile, it does exactly the same. So if you make an assumption of no anisotropy, you're adjusting for that drop by changing your density profile, but you can also do it the other way around, right? So and that has the biggest impact on the H0. So it's effectively assuming either you're changing the density profile to match your kinematics, or you're changing anisotropy, and they are degenerate with each other, and that's what you exactly see there. So we need to break that mass density anisotropy degeneracy.
Thank you.
Okay, I think unless there's any pressing question, I think we should one last question then here, and then there's a technical problem, so we cannot go on with the next talk as of yet. So we will break for coffee now and probably reconvene earlier than what's scheduled. But yeah, please.
Can you tell me about the different photons you receive, say from the left side and the right side? They will be entangled quantum mechanically. When you measure, suppose you measure the status of the left photons, will you see any effect on the other one?
Well, not at this level. I mean, this of course is right. The time delays, just to put it in perspective, are weeks or months or sometimes years, right? So what we're really in the standard, let's say, regime, and not in the quantum regime at all. Right, what you're actually measuring is simply a wave front moving outward and being bent. So you can look at it in different ways, but effectively what's happening is you're just looking at completely separate photons. But you have a big, let's say, region of material that's sending out light, is getting brighter, but they are actually different photons.
Yeah, the number is too large. It was an idea of John Archibald Wheeler.
No, I mean, but you're right. For example, in gravitational waves, you can find effects of interference, but in the wavefronts, etc. And people are very interested doing that in lensed gravitational waves. But in this regime, that's completely impossible. Yeah.
Okay, I think we should stop here.